Good afternoon, everyone. I hope you are doing all right. So, last class we talked about waves, how waves are generated, and we also learned there are mainly two types of waves, one being longitudinal, another one is transverse. So, today we will be talking about the example of those two kinds of waves. And example of longitudinal wave is sound wave, and sound wave also generates because of the vibration of some sort of source, right? So when I'm speaking, there is something in my, uh, like vocal cord that's vibrating, and because of that oscillation or vibration, is producing sound wave, and it transmits through the air, and it goes to the microphone. So when we are listening some sound from, for example, some sort of device, they have speakers, and there is that membrane that vibrates in the speaker, right? So the oscillation is generating sound wave. Oh, my pen doesn't want to write. That's not good. So anyway, you can see on the left side of the screen, there is that pictures of a speaker. So what happens? There is this membrane that vibrates, and that's what produces sound. So when we look at the plot of sound wave, it looks like a transverse wave plot because it's going up and down. But in this case, notice we are plotting the change in pressure. So what happens when these molecules are close together? Pressure becomes larger. When these molecules are a little farther apart, what happens? Pressure becomes smaller. So pressure changes when sound is transmitting through the any media. Okay, so that's what the plot you see here, and how fast sound moves in a medium depends on density of the medium that you see here in the denominator of this equation, and the elastic property. Okay, so how quickly the molecules are recovering from disturbance, right? If they are recovering faster, we say, okay, they have higher elasticity. And for gases and liquid, the elasticity, remember for the spring elasticity or elastic constant was K. Similarly, for the solid object, it was Young's modulus. We talked in physics 1. I did not talk about bulk modulus in physics 1, but here that's what this is. Okay, so this is elasticity mostly applicable to the gas and liquid. So for the fluids, for example. Okay, so that's how we visualize the sound wave as well. So it looks like any typical wave, just like we talked in last class, right? So in this case, it is moving to the right as indicated by the arrow V. Okay. So now when we are listening sound, yeah, my computer seems to be actually frozen. It's not just a pen. Okay, sorry about that. Hopefully it works now. So now when we talk about sound, basically when wave is moving, is transferring the energy, and rate of transfer of energy is called power. We define power as change in energy over time interval. Probably you remember from physics 1, right? Now intensity is like, for example, let's say I have a microphone and it has certain surface area. So how much power it is receiving per unit area is the intensity, right? So if it's receiving more power, more intense. And it's not just for the sound wave, it is also for the light wave. So for example, if you have powerful light bulb, what happens? You see the surface gets brighter, okay? And the brightness increases if you go closer to the source, right? So smaller the R, the intensity is larger, and it is R squared in the denominator. So when we double the distance, the intensity gonna be 4 times smaller, but if we go halfway, then it's gonna be 4 times larger. Even the source is same, so the power is source related, and intensity is what we receive, what we perceive, what a particular surface area receives, and that's what the intensity is. Okay, so intensity is related to loudness as well. So intensity purely mathematical description, and intensity of a wave, something like this, we learned that this is called amplitude, right? From mean position to maximum displacement is called amplitude. Maximum displacement is the amplitude, right? So intensity of any wave is square, is proportional, I should say. There are other things that it depends on, but it is proportional to the amplitude. Now, if we are plotting pressure here, and then this amplitude is going to be the pressure amplitude. So that's what I'm writing here, P0, just like we used to write A for the amplitude. Here we are writing P0. Okay, so pressure amplitude. So when plotting, we can plot the pressure change, and we can also plot how the air molecules, for example, from rarefaction to let's say, yeah, from rarefaction to rarefaction is one wavelength in that case. Okay, so we can look at the displacement as well. So how far it is displacing. Okay, so the distance between, from let's say middle of the rarefaction to the middle of the compression, we can think of that as a amplitude. So that amplitude is going to be displacement amplitude, so pressure amplitude. So why we have two kinds of amplitude? Because this sound wave can be represented something like this by plotting in vertical axis. We can plot either change in pressure. When we are plotting change in pressure, then that amplitude gonna be a pressure amplitude. But if we are plotting the position of the oscillating molecule, that is oscillating parallel to the motion, then that becomes amplitude. So this amplitude is actually like our usual amplitude we've been talking about. Okay, so in this case we are looking at the amplitude of the air molecules that goes left and right when sound is traveling in a particular direction. So this is oscillation of air molecules, for example, in the case of sound wave. Okay, and of course what's going to happen? Uh, so both of these are amplitudes, and if the displacement is large, then the pressure amplitude going to be also large. So they are directly related, and the relationship has these couple of things. For example, this is displacement amplitude and this is pressure amplitude. So pressure amplitude is not equal to the pressure amplitude, but what happens? There is this density of the medium. So for example, if we're talking about gas, then that's going to be density of gas. If we're talking about sound traveling in water, then that's going to be density of water. And of course, this is going to be speed. And this is the frequency. So angular frequency, we can write that in terms of linear frequency if we like, something like this, right? So this relationship, I think you are familiar with from physics 1 as well, this one, but this one I'm just introducing. So basically what happens is here intensity is proportional to the amplitude square, and there could be two different kinds of amplitude when we talk about sound waves. So that's what you want to keep in mind. And the intensity in terms of pressure amplitude can be written something like this, right? So it is proportional to P0 square. So when we convert this proportionality sign to equality sign, we have some proportionality constant, okay? So that proportionality constant in this case happens to be 1 over 2 times density times speed. So for a particular density, gas or water, the speed gonna be fixed. As we saw, speed is given by B over density, right? So this is elasticity divided by density. So for a fixed density, the speed also going to be fixed. So they are basically related. And that's how the intensity looks like in terms of the pressure amplitude. But since the pressure amplitude and the displacement amplitude are related, so we can replace this P0 square or pressure amplitude square by substituting this one in that equation. When we do that, and that's what we pick up, and you still can see this is basically there is S0 square. Looks like there is one extra density that can cancel from numerator and denominator. There is speed that can cancel. So it gives you this equation. So the amplitude can be calculated, or sorry, the intensity can be calculated if you know what is the amplitude of the wave. So if you are given a plot of a wave, then you should be able to calculate amplitude. So yes, so this sound intensity is purely mathematical quantity, and intense sound also means loud sound, okay? But our ear, our hearing mechanism cannot interpret that very large range of intensity that we get from this mathematical equation. What happens is it processes in a squeezed band. Okay, so for example, we say, okay, this is in log scale. Our listening or hearing is in log scale, and that's what we are defining here. Okay, so what we perceive is not the intensity, rather we perceive the loudness. Okay, so loudness depends on intensity, but our ear basically hears the in the log scale, and we define that as a loudness, also called sound level, same name, and notation for that is beta. Okay, and you can see this is the ratio of two intensities, and this I0 intensity is a constant. What is it? It is the intensity at which our normal ear, that we haven't abused yet to loud exposure of loud sound and so on. If our hearing is intact, what's going to happen is our ear can hear this much intensity. Okay, smallest intensity it can hear or detect or notice is that one. So that is, so what kind of sound is that? So sometimes you may hear leaf kind of little bit, ruffling a little bit slightly, not, you know, uh, with a like blowing air or something like that. It may be just, flickering a little bit. In that case, you may hear very faint sound. That is kind of about this much intensity. So if I were to plug that one here, what happens is this ratio becomes 1. So in that case, we see we have this beta value coming out as a barely positive value. Okay, so kind of 0, slightly above 0. That's when we can hear. So it's called threshold of hearing. Okay, so still this intensity is not, cannot be heard, but if we go anywhere above that, we can hear that. That's what it is saying basically. Okay, so if we want to find what's the loudness, then we can calculate this one here. And for a given intensity, what happens? This I0 is fixed. So you put that, you take the ratio, and then you take the log of that. And just like you take sine, cosine, log is also found in your calculator. But there are two kind of log. One is log, usually written as a log. It has a base 10, and another one usually written as ln, which has a base e. And so in this case, while calculating this, you want to make sure that you are using the log with the 10 base. Okay. So now, if you are given one value of intensity, and then you are given another value of intensity. For example, let's say you are given 10 times 10 to the power negative 12. So 10 times larger than the what we can, what's the threshold of hearing is. And then let's say you are given 100 times 10 to the power negative 12, and unit, I'm talking in terms of watt per unit, watt per square meter. So if you are given these two values, what you can do is, okay, you get the new and you put the old over here and calculate, and you can see this one, although you may see this went from 10 to 100, right? See, 10 to the power negative 12 is still same, means it went like 100. But when we take log of 100, what happens is it is just 2. Okay, so although in linear scale, in intensity scale, it went 10 times more, here what happened? Log of 10. Oh, this is just 10 times more, not 100 times. So this is just 10 times more. So that means log 10 of 10 is just 1. So what happened? Change in intensity is 10 decibel. And you can use any number here, 1000 for example, and plug in those. So that's how this formula is used, folks. So here is a related question. So it says sound level of 20 meters from a loudspeaker. So distance is given, and sound level, of course, remember the intensity depends on the distance, means loudness also depends on distance. Further we go, loudness decreases just like intensity decreases. Just like light becomes, light, what you can see when you are closest to the light versus when you are moving farther and farther of light, what happens? Your hand, for example, in this case, is receiving less and less light. Okay, less, so intensity is getting smaller. So similarly, the sound also becomes, of course, decreases and eventually becomes inaudible, right? So we cannot hear what's going on after that. So that's what it's talking about. What is the rate at which sound energy is being produced by the loudspeaker? Assuming it is to be an isotropic source. So isotropic means, you know, it goes equal amount in all direction, okay? Transmitting equally in all direction. So it doesn't matter. So this is 25 meter from a source, right? So it doesn't matter whether you are measuring here or here as long as distance is 25 meter. So that's what that isotropic means there, okay? So what is the rate at which sound energy is being produced? So here, the decibel beta value is given, okay? And distance is given. But we know distance is related to intensity, which is related to this value. So that's why we need to start from this equation here, because this beta is given, which is 71 decibel. Okay, so now, so that means we can find intensity, and then we can find the power, and power is the rate of transfer of energy, okay? Rate at which it's being produced. So it is producing in that rate and then letting it go at that rate. So basically it's talking about power, okay? So to find power, you need intensity, okay? So that's where this equation, when we use this equation here, now what you see is this beta is 71 decibel, means now we can solve this equation for the I, because I0 is constant number, so we can just use that from there, right? So I think I0, yeah, I don't write too much. I think it is negative 12 watt per square meter, okay? So we know that. So that means from this equation, we should be able to find the I value. And now here, I just move this one. So decibel, decibel, this unit cancels. So we are getting just that. Okay. So now we have to find intensity here. And log is over there. So we need to get rid of that log. So to get rid of log, and this has a base 10, so that means we can write this I over I0 as something like this, okay? So this is just a little bit log mathematics. It comes from the definition of log. And now I is simply I0 times this thing here. So I0 we know. So by plugging in that number, 1.0 times 10 to the power negative 12 means simply, basically 10 to the power negative 12. So that's what I'm writing here. So that gives us that watt per square meter. Okay. So now we have intensity. Now we can write the power, find the power, right? So the power or the decibel level we received was at 25 meter. So we can use that. And by the way, this area is, see, the area of a circle is pi r square. But when sound travels, what happens? It goes in all direction, up, down, left, right, in all directions. So it is like a sphere. So this is for circle, 2 dimension, but sound travels in 3 dimensions. So that's why we need to use the area of a sphere. So once we do that, what happens? We can find the power. So that's how we can use this formula, and you can go all the way around if you know power, and then you can figure out, okay, what's going to be the decibel level at a certain distance. You can calculate that, okay? So first you need to find intensity and then plug that intensity in this equation over here, this equation, and that's going to give you sound in decibel level. So in this case, we found the power. So I went that way because maybe we forgot to, this rearrange this log thingy, right? So to remind you, I did that. But if the power is given, you can figure out intensity, and this one, the calculator calculates the log of any number, so you can do that. Okay, so that is about the intensity and the loudness of the sound. Now let's talk a little bit about bits, sound bits. Okay, uh, I have a video made by a professor. So he's talking about, hopefully the sound works. Okay, it does.
I don't know if it's just me, but I can't hear anything.
Hey, my chat was hiding. Okay, so microphone, so you can hear me, right?
Yes, I can hear you, but I couldn't hear the video.
Oh, that's interesting. So microphone's supposed to pick that, and you should be able to hear that. That's not good. I wanted to hear that. When they are not emitting same frequency, then that's where you hear that beat. Okay, so there is one frequency of one sound that's coming from plucking one string, and there is another frequency, and they are slightly different. And because of that, when both of them are getting plucked, what happens? You hear combination of both, mixed one, okay? And that's where you hear that repetition kind of is now slower than the original sounds, but it sounds a bit weird. Notice if you can hear that. So one frequency, so now they are not matching. Because of that, you hear that reverberation there.
it'll be in tune. There, now it's in tune. Okay.
Okay, so why does that happen? So mathematically, we can actually derive the equation that's going to give you the frequency of the bit. So the derivation involves a little bit trigonometry, and we have to use trig identity. I don't know if you are familiar with this trig identity, sine A plus sine B, and that comes out as something like this, right? So this is basically identity. So that means we are adding this one, see, one sine, another one sine function here, right? And when we add that and do little algebra using that identity, we can get this. Here, this omega is 2 pi f. So here it's written in terms of frequency f. Here it's written in terms of omega because it becomes, it has already become messy. So, uh, you know, combining this 2 pi and f1 together makes more sense here. So you see here, there is this difference here, omega minus omega 2, and that is directly related to f1 minus f2. So graphically, if we try to understand what happens, see, here we are plotting time. So last time when we looked at the wave plot, it was position x. Now we are plotting time. So how about position? So we are just picking. So in this case, we are picking a point. For example, let's say a string, how a point of the string is vibrating up and down, okay, with time. So that's what it is representing. So in this case, peak to peak value gonna be the period, and 1 over period is frequency. Okay, so peak to peak value is period, and 1 over period is frequency. So you see the period of the red wave, which I'm saying, okay, the frequency of that one is f1. That is slightly smaller than the blue frequency, f2. So red is repeating faster than the blue. So that's why f1 is a bit larger than the blue. Or another way to look at, I think that is the better way. So now what happens is these are superposing. So we talked about principle of superposition of waves last class. So what happens here? This peak is almost matching over here. So that's why you are getting this, over here, these peaks seem to be kind of matching over there, very close. So that's why you get the highest amplitude here, 2 times A. But if we come over here along this line, what do you see? See, one red is, has a positive amplitude, and blue has a negative amplitude. And in that point, at that point, what happens? It has become 0. And all other points are like, there are these maximums and zeros, maximum and zeros, and all other points are in between. So now, for this one, if you wanted to find frequency, you would do the period here and divide period by 1. You take the reciprocal, right? So that's how you'd find the frequency. Over here, you do the same, but now you see the time period is a lot longer. So that means frequency is now smaller. So that's why the bit frequency is not equal to f1, not equal to f2, but it is difference between them. And that's how the frequency of bit is calculated. Okay. So mathematically, this wave is written something like this. And how the amplitude is changing here? The amplitude is not just 2 times A, which is the maximum value, but now the amplitude depends on frequency as well. See, it has a frequency inside this cosine thingy, okay, difference in frequency. So the amplitude depends on difference in frequency, and difference in frequency is the bit, okay? So that's what it is talking about. So if you don't understand this mathematics, I didn't go in detail, that's fine, but understand the bit phenomenon hopefully now, and how it works, and where the formula of the bits comes from, right? And of course, formula of bit is really simple. You just take the difference, right? So now here is a question for you. I think for this question, a minute should be good enough. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got here. So mostly A. So that is correct answer. That was the video was about. Uh, okay, so I just noticed there was a question on the message, which I have an answer. I will do that, but before that, let's pull the second one I have here. So now I'm pulling on this one here. Okay. So this one this time. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. So mostly C, that is correct. So we take the difference between two source frequencies. Okay. So looks like my chat wasn't set up for writing message to everyone. So these messages came as a private message. So the question was, I cannot seem to send a message to the whole class, but does the sound wave vibrate the air molecules, and that's what causing the air molecules to oscillate? Yeah. So this is kind of a bit complex, right? So there is a string, that's what you are plucking, And then when a string sets up in vibration, it sets up the board, that wood of the guitar in vibration. And once that whole body is vibrating, the air inside vibrates, and then that's where the sound is now coming from. So that's like our vocal cord, the guitar. Okay, so that's how it happens. Yes, so you are right. Okay, so now what happens is a instrument, for example, a guitar, one string of a guitar can produce a pure tone of particular frequency or combination of frequencies, higher harmonics. We talked about that last class, right? Depending on how hard you are plucking, how hard you are blowing, you can get different harmonics, right? So there can be different frequencies. But let's say even if there is only one frequency, but if either the source of that frequency or the observer or both of them are moving with respect to each other, what happens is what you hear is different frequency than what it is coming from the source. So probably you may have noticed or you may not have, but next time when police car with the siren or the fire truck with the siren passes, ambulance with the siren passes, what happens is you can hear two things, two different phenomenon there. One, loudness is changing. Of course, when it is coming closer, loudness increases. But so that is obvious. Okay, it is like intensity is inversely proportional to the square of the distance. So that's the loudness or intensity, right? But if you pay attention, pitch of the sound also changes, means frequency of the sound also changes. So when it is approaching, what happens? When car is, for example, approaching, the frequency you hear is higher than the frequency that's coming from the source. So it is because of the relative motion between observer and the source. So here observer is this person. So for example, when let's say something is moving while emitting the sound, what happens is that it's like a emitting sound is like a emitting ripple in the water. I'm sure you have tapped on the water surface, right? If you do that repeatedly at one point, what happens? You see nice spread of the this and they are equally separated. Okay, so these are like a wavelength. Okay, separation distance between two peaks are the wavelength. But when you are tapping here but also moving, let's say in that direction, then what happens? The tap from this one, when you tapped it here, the original wave has already reached over there, and the one that you tapped from here is now approaching there, and then this one just coming out. So what happens is they become crowded, and the side, the source is moving. But on the other side, they become not crowded because they move with the same speed in all direction. But think about this kind of, this circle is moving. Source moving means circle is like moving, okay? So that means when it is moving in that direction, the separation is going to be larger here compared to the separation over there. So that's the effect you see here in this sketch. And I had linked this video for you in the pre-class exercise, I think. And I grabbed a screen from that video and put two screens together here. And you can see when car is approaching, this portion is arriving. So that means frequency you hear is larger. When car is leaving, what happens is that now you are hearing this part here, means now wavelength have become longer, frequency is now So wavelength shorter means frequency higher, and wavelength longer means frequency is smaller. They are inversely related, wavelength, frequency and wavelength, right? So here car is moving with certain speed means source is moving with certain speed. So frequency is V over wavelength. So wavelength and frequency, they are inversely related. So that's what the Doppler effect is. And Doppler effect is not just for sound wave, it happens for the light wave as well. And their wavelength, the wavelength of the light that we are receiving sometimes may be different. For example, we may be measuring some sort of red light coming from some object, let's say, uh, in the sky. So frequency of the red light when the source is not moving, it has one value, and we know that. But if you are receiving frequency, higher frequency, that means that object is moving towards us. So that means if that thing happens to be, let's say, some sort of, asteroid or comet or something like that, so in that case, we can tell, oh, now it's arriving. Before we can see it, right? We may be able to detect that Doppler shift using these devices and tell, oh, it's coming. Now, if it is coming, then what rate it is coming, what speed it is moving, right? We should be able to calculate that and tell when it's gonna, let's say, arrive to the Earth and gonna, let's say, hit the Earth or it's gonna miss the Earth and so on, right? So this Doppler effect becomes very useful, and the police also uses this Doppler radar to figure out how fast you are moving and that's what they use. Okay, so here we can write that equation between the frequencies that actually is the source at rest would emit versus the frequency that we hear when either source or us are moving. So in that case, what happens? Sound is moving. Sound has a one speed. We call that V. Okay. And then there's going to be speed of the observer. If, for example, you are also driving, then you are moving too, right? And then there is speed of the source. So that means it is the speed of the, let's say, ambulance. So that means we can have, so if we collect all of those, we get this equation. So if you look at the note, I have written something like this. I have included both positive and negative sign, okay, in that equation. But we can also just say, okay, there are these negative signs, and now this V0 and Vs means speed of the observer or the speed of source. They so rather than saying speed, maybe I should say velocity. So we can have the sign of these velocities as well. So how do we take account of that? So for that I have written this here. So either source or velocity, sorry, source or the observer, you know, take that as a positive when they are moving in the direction of the wave propagation, right? So for example, in this case, what happens? The source is here somewhere that, it's not visible. So source is somewhere here, let's say. That means sound is coming to our ear means sound is moving this way. And then sound wave is moving this way. And the ambulance, for example, is also moving that way. So that means that's going to be velocity of source. In this case, this person is not moving. So velocity of observer is 0. But if this person was moving this way, then we could say, okay, that's the velocity of observer. Now, here, what it is saying is they to be positive when they move in the direction of the wave propagation. So for example, in this case, what happens? Source is moving in the direction of wave propagation. So that means whatever the speed of the source is, let's say 15 meter per second, and that would be positive in this case when it is, you know, moving in the same direction as the sound. Okay, but now let's say here when it is on this side, what happens? The source is moving this way, so velocity of source is still that, but the sound that we are receiving in our ear, it is moving that direction. You see that? So because of that, in this case, they are moving in opposite direction, means when we are calculating a frequency for this case, we need to take this velocity, source velocity, as a negative. And when we are calculating frequency over here, we need to take source frequency as a positive over here. And that those signs are on top of this negative sign already we have. Negative sign is in formula, and then this velocity is can also have positive or negative sign. And I find this way a kind of bit easier to figure things out. Okay. So in this case, observer is not moving. So velocity of the observer means this is going to be 0. And if this was positive 15, then sound speed is around what, 340. And then now let's say if that is 15, positive 15 means negative times positive would be this. And here this is 340, for example. Okay. So now you can see this is smaller than 340. So that means this number, this ratio going to be larger than 1, means frequency observed by this observer going to be larger. And exactly opposite happens here. Over here is going to be V is negative 15 meter per second. So that means over here, this negative and that negative becomes positive. And this gets added, means this number, denominator, is now larger than numerator V, means this frequency we calculate going to be smaller. Okay. So I think I have problem here. So in this case, it says source of sound frequency that many hertz. So frequency of source, let's say Fs, is 1 kilohertz, means 1000 hertz, or 10 to the power 3 hertz. Okay. So the source of sound and speed is 0. It's stationary. What is the observed frequency if the observer moves towards the source? And where is the speed? So observer is traveling 0.5 times the speed of sound. So in this case, looks like moving fast. So observer speed is 0.5 times the speed of sound. We denoted that by simply V, okay? Half of the speed of sound. So 0.5 times V. So this way we don't have to know what's the velocity of the sound wave, okay? So now what is the observed frequency if the observer moves towards the source? Okay, so now source is here and observer is here. Okay, so observer is moving that way, sound is moving this way. So B is this way, observer is going that way. They are in opposite direction. So what that means? That means velocity of observer. Since observer is moving opposite to the remember what happens is if two objects are moving close to each other, relative velocity becomes faster, right? So if you are driving and another car is also driving, and then in that case, what happens? The relative velocity becomes faster, means you're going to be approaching faster. But if both of you are driving in the same direction, and then even if you are driving faster than the other person, to catch that car is going to take a while. Okay, so that is called relative velocity. So here, this is the relative velocity between sound wave and the observer. Okay, so they are moving towards each other, means they have to be, the relative speed going to be larger, so they have to be added. So for that, to use that in our formula, we have to use negative sign. Source, we use V0 as a negative of 0.5b. Okay, so we're going to put negative and plug that in this equation. But if you are using this equation, then you're gonna pick the one with the positive sign because the relative velocity is larger. Okay, so now we have that V0 and Bs, and B is B. So that means B received by observer gonna be, given by this formula here, B minus B0 over B minus Bs times the source frequency. So now Bs is 0, means this is 0. So that means we have B minus and minus 0.5 B over B, and this is Fs. So now let's see how does it simplifies. So this negative and negative becomes positive, and this B plus half V means how much? 1.5 V, and divide that by V, and there is Fs, so V cancel. See, we don't need to write the value of the velocity this way. So looks like the frequency becomes 1.5 times the source frequency. So source frequency is 1 kilohertz, means this observed frequency is the 1.5 kilohertz or 1500 hertz. Okay, so that's how we use this formula. And there is part B, and I am asking you to repeat this with the observer moving in the other direction, means opposite direction. So that means observer is also moving that way. So you are driving this way and car is approaching to you from behind. So now in that case, what happens? V0 has to be positive 0.5 V, speed of the sound. So there are three different speeds, so make sure to use them wisely. So I'm just gonna leave it here. It's the basically same problem now, it's just a positive 0.5. So that means the result gonna be less than 1000 hertz. Okay, so with that, it's 3:04. So I think let's take a break, and we're gonna move away from the sound. Okay, folks, welcome back. So that was sound wave, a longitudinal wave. Now let's talk about electromagnetic wave, which is example of transverse wave. And let's see.
Is what gives
Let's
rise to
place
light
here.
waves. And quite often, these ideas are useful in.
So this clip is from a channel called Blue and Brown, 3 blue and 1 brown, something like that. Okay. So here I wanted to point out just this animation, And notice how there are these oscillation taking place. So there is, if you follow the blue arrows, it has one sinusoidal wave. And then now there is yellow arrows. See, that has its own pattern. So in this animation, what's happening? These blues are oscillating up and down, but the yellows are oscillating sideways. So if you think about, let's say, this is drawn in 3 dimension. So think about corner of a room, right? So in a room, if you go to the corner, then you see there are 3 lines, one horizontal, another one is also horizontal, and there is one vertical, right? So in this case, what's happening is these two are oscillating in 2 different planes, like along 2 different walls. One is oscillating along the, let's say, vertical wall. Another one is oscillating along the floor. Okay, so that's what they are doing. And at the same times, they are also moving. And perpendicular to both means it's like uh, so 3 lines in the wall. So those you can think of 3 axes, 3-dimensional axis, and that's what happening. So one is moving along one of the axis, another one is moving another axis perpendicular to it, and both of them are, they are oscillating like that, but at the same time they are moving perpendicular to each other. Okay, so that's how this wave moves. And I think I have a sketch. So this was the animation. So let me run this animation a little bit. So if you are interested, please pay attention. It goes in a second.
Is what gives rise to light waves. And
You
quite
have, they are
often, these ideas
oscillating.
are useful in
Okay. So I thought I brought my sketch, but I think I just left that in the note. So I have a question for you over here. E field means electric field, B field means magnetic field, okay? So what do you think based on what you have learned so far? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So B field, yes, that's what we have seen, right? When current passes through a wire, we point thumb in that direction and B field crawls, right? So that's what we have learned so far. But it turns out it could be either one of those, okay? Electric field can also circulate, and that's what we're going to talk about, okay? So this one is Faraday's law, we already talked about. So since, you know, we want to connect this idea, and so I'm repeating that one here. So induced EMF, oh, it changed the font, did not it? It's supposed to be EMF, and notation was this. So EMF is given by rate of change of flux. So for example, in this case, North Pole is moving towards the coil, once it coming closer, flux is increasing. And to oppose that, there are going to be induced current. And the induced current, since the induced field, the field needs to be induced this direction, the current going to be circulating something like that as shown by the arrow over there. Okay, so that is Faraday's law and Lenz's law that has a negative sign. That what the idea of the opposing thingy comes in. Okay, so now what we can do is we can write this slightly differently. So EMF and electric field, they are related. I think I have written it here. EMF and electric field, they are related. This is what we learn. Yes, there is negative sign as well in the formula, but I'm ignoring that negative sign here. Negative sign simply means direction in this case because electric field is a vector quantity. So that means delta V, or potential difference, can be written as a product of electric field and the distance, or delta X. Okay. So now, so that's why this EMF, I'm writing something like this. So why I need to write summation sign here? And delta L here is the length of the wire. Think about something like this coil, right? So this coil is in magnetic field, something like this. So when magnetic field is changing, the current induces, we learned that, right? So whenever there is current, that means there is EMF, there is field. So how are the field acting here? So in this case, field is perpendicular to the, tangential, I should say, tangential to the coil at any point. Just like a magnetic field and field lines, remember they are perpendicular, I mean tangential. Same thing goes here. So we can say, okay, electric field lines are circulating like this, and this is electric field. Just like magnetic field, we learned magnetic field lines can circulate, and magnetic field at any point is given by a tangent. So same idea. We are just inducing that, okay? So if I want to write those electric field, then I need to go from this EMF to the electric field, and this became box. It's supposed to be parallel. So since it is circulating, what we do is we look at the small segment of wire, that's what the delta L, and there is this electric field. So now for that small segment, this electric field and delta L, they are in same direction. Okay, so that's what we are doing. And now if I were to collect all of them and then add them together, that's going to give us the whole loop. Okay, so that's what it means. So it represents this whole loop here, loop of the electric field, let's say. Okay, so now this being a circle, this delta L, so here electric field is direction is changing, but the value is not changing. So we are basically summing the length here. Okay, so that means this length of this wire gonna be same as the circumference of this coil. So we can write that in terms of circumference. So what I did was I kept the E over here, electric field. And by the way, this was EMF, and this is electric field, and this is electric field. So I brought that 2 pi r over here, and that's what I'm writing. Okay. So electric field can be written in terms of electric field circulating in a wire, or electric field loop can be written something like this. And so what happens is, even if there is no conductor, the electric field could be circulating just like a magnetic field. They are circulating without, like let's say at the space there may not be any wire or anything like that. Magnetic field can circulate. Similarly, this electric field can also circulate. Okay, so that's what that the previous question was about. Okay, yes, of course we hadn't introduced the circulating electric field, so that's why many of you missed that. So now you know it. So now, so going back to what we had here, so that was the Faraday's idea, right? Flux is changing in a loop, so that induces this circular field like this. So now what another scientist named Maxwell did was, okay, so if changing flux can generate circulating electric field, then maybe changing electric flux. So see, these are shown as electric field between the plates. When charge in the plate changes, so when you change the current, charge gonna change. So when charge changes, what's gonna happen? The flux gonna change. Just like when current changes over here, magnetic flux changes over here. Similarly, we can think of when current changes, charge changes. When charge is changing, the field, you know, the flux changes here means it's gonna induce circulating field. So before we learned that when current is flowing through the wire, they're gonna be induced electric field, sorry, magnetic field. But now Maxwell saying, okay, since we can see this electric field over here, we should also be able to see this magnetic field over here. Okay, so now that's where this idea comes from, that okay, so there is changing current or changing charge can change the flux, and that can generate the or induce the changing electric field. Similarly, changing charge can also induce the magnetic field. So that process, what happens is basically even after that charge is not there, what happens now? This changing electric field can induce changing magnetic field, and changing magnetic field can induce this electric field back. So that way we get the oscillating magnetic and electric field, and for them to oscillate, we don't need any source, and that's how uh, see, I typed all these equations in different computer, and now I'm teaching you in using different computer tablet. And because of that, what happens? All the font got messed up. So these are parallel, and this is mu naught, which is good. And this is supposed to be epsilon naught, electric permittivity. Okay. So just like we can write this equation, we can write this equation, which tells us the induced magnetic field due to the changing electric flux. So now, so that means there is changing electric flux, and induced magnetic field means there is a current. So we had one kind of current that induced the magnetic field. Now there is this different mechanism that is also contributing to the induced magnetic field. So we can think of there are two kinds of current, okay? And remember, this was the Ampere's law we already talked about. So there is one kind of current that produces this magnetic field. Now Maxwell is proposing that we have this another kind of magnetic field that's being produced by changing flux. So you can think of that as also a current. So two kind of current. So now you can say, okay, this is current in a conductor, in a wire, and you can think of this as a, I think they call it displacement current. Okay, so epsilon naught is here. Sorry about mess with this. I think on the note, I printed that, you know, the slides in another computer where I made these slides. So I think the fonts on my posted slides should be fine. Only here in this different computer, it's not showing those certain points. Okay, so we have one current that can produce our good old magnetic field, and now we have another source, and this equation is called Ampere's-Maxwell equation. So Maxwell bundled this equation with the other ideas, and that forms the basic four equations, which basically we talked about them here, not in one place, okay, but slightly different ways. But for the physics measure, we put together all these equations together and then derive the equation for these fluctuating or moving wave, okay, wave equation. So here for this class, we are just you want to keep in mind that, okay, what is electromagnetic wave then? Electromagnetic wave is like a family of light wave. The light we see, it is also electromagnetic wave. Sound is not electromagnetic wave, okay, but the light is. And there are other electromagnetic waves as well. So there are different kinds of waves. They are categorized based on their wavelength or frequency. We'll talk about that. But first, what you want to keep in mind is that when light is traveling or any electromagnetic wave is traveling, there are two kinds of oscillation. One is electric field that's oscillating, indicated by this axis, right? And then another one is oscillating in this direction, just like you saw in that brief clip. And then it's propagating in that direction, both of them. And what happens is you don't need source anymore. Once they are generated, they detach from the source and then move, right? So for example, when light is coming and hitting my face, hitting my paper, hitting my table, remember it already left the source, right? So source wasn't there, so just it's the light that was moving. So what is moving? How was it moving? So if you are curious, then this is what happening, okay? When source generated, it generated oscillating electric field and oscillating magnetic field. Now they detached from the source and started moving. And in the process of moving, they are still oscillating, but at the same time, they are also kind of, regenerating itself and then moving, okay? So their equation can be written something like this. See here, we are writing in terms of electric field, but we can do that for the magnetic field as well. We can write the similar equation. And if you are thinking what this equation is, we wrote the wave equation yesterday. And that was something like this: y is equal to a cosine, I think, kx or omega t. We may, write whichever we like first here inside the argument. It does not make any difference because cosine of negative theta is same as cosine theta. So I think last time we wrote something like this: omega, I think we wrote first, and then kx. Okay. So this is the traveling wave equation we wrote, and this is also a traveling wave equation. So over here, these particles were vibrating, but here, these are the fields that's vibrating, electric field and magnetic field. So they don't need medium. So for example, if there is no medium, you cannot hear sound. So for example, if I am sitting in a room and speaking and you are in the same room and you are listening me, so what happens? You can listen because there is air. If the room was vacuum, you couldn't hear, okay? But light can travel without any kind of medium. So that's neat. So that's why, that's how we are receiving light from the sun. Otherwise, there is no medium in between sun and the earth. There are a few hundred kilometers, there is some air. Then after that, this atmosphere kind of becomes so thin that it becomes negligible. So there is nothing. It's a vacuum between moon, sorry, not the moon, but the sun and the earth. And what happens? We receive light. If light was like a sound wave that needed medium to travel, then we wouldn't be here on the earth. Remember, all the energy we get is from the sun. So if that energy did not arrive here because of the absence of the medium, then we wouldn't be here. So isn't that nice property of these electromagnetic waves or radiations, right? So that's what that is. So this K is just the name for the 2 pi over lambda, also called wave number. And this is angular frequency you are already familiar with, okay? And then that's how, the Maxwell was able to tell, okay, light is also part of electromagnetic radiation, because at that time speed of light was already measured, okay? And then combining those four equations I talked about, Maxwell was able to figure out the speed of the light or electromagnetic wave. And remember, it's supposed to be epsilon, not here. So the equation turns out to be this. And since this is constant and this is also constant, so that means the speed of light in a vacuum does not depend on anything else. And it's a fixed number. And that number is this. And often light speed is denoted by lowercase c. Okay. Uppercase c we use for capacitance. So lowercase c is the notation for speed of electromagnetic wave or speed of light. So often for the speed we use v, lowercase v, right? But when it is electromagnetic wave, it is fixed, we know, and because of that, we use lowercase c to denote it, okay? And these oscillating electric field and magnetic field, they are related to each other through the same c. Oh, the c is here. So that is E times CV. Okay, so this is the introduction of electromagnetic wave, and we see light has different color, right? So when you decompose light, you can see rainbow, 7 colors, right? But there are other invisible. And why we have different color? Because each color has its own wavelength. They have different wavelengths. So different wavelengths means different color. And since wavelength and frequency are related, C is now f times lambda. So we may talk in terms of wavelength, or we can talk in terms of frequency, because C is fixed, means once we know wavelength, we know frequency, because C is fixed. So we can calculate that. So that means we can talk those colors in terms of wavelength or frequency, but they are inversely related. So when wavelength is increasing, frequency is decreasing, and so on. So collection of all kind of color. This is visible color on the white light, but there are other invisible as well, invisible light or different kind of radiation. So we divide them, categorize them based on their wavelength or frequency. So one that has thousands of kilometers is radio waves. Remember, we used to listen radio, you tuning into AM radio. These days, often radios are FM. Oh, these days, internet mostly. But before internet, it was FM. But before FM, it used to be AM. So that's how they were broadcasted. Okay. And of course, the FM is also within this radio waves, but in shorter wavelength. Okay. So often, I think you may have heard, if you tune in FM radio in your car, and then usually they say, okay, we are broadcasting in this much megahertz. So that means the FM radio is in this region, and AM radios are even before that. And then microwave, I mean, used to, the way microwave we use to warm our food. We don't eat microwave, but we warm food. So that is in this region. And after that, infrared, okay, that is the heat radiation. Uh, And then comes the visible. This is the very small portion. See, only very small portion of the wavelength our eye can detect. Okay. And then there is UV rays. Probably you are familiar with that, harms our skin. And the X-rays, you are familiar. The gamma rays, they arises from the nuclear reaction. So that's not very often. But X-rays, gamma rays, they are very energetic. So we have to be careful handling them. Even the UV can be harmful, right? But microwaves and radio waves, they are not harmful, rather very useful. Oh, I'm just noticing there was this different part of the wavelength these different devices use. Okay, so cellular phone uses the highest frequency or the shortest wavelength among them. Okay, so what do you think of this question then? 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So yes, it is the color, different color we see, not the different brightness. Okay, brightness depends on amplitude, not the frequency. And amplitude and frequency, they are different thing. You know now, right? And by the way, before I forget, before I let you go, so pre-class assignment for next class, for the Tuesday's class, gonna be coming hopefully by tomorrow. Okay, so the questions are still not ready. I'm still kind of in the process of, writing them. So probably I may have said you earlier. So this semester I'm making changes in the note and providing class notes to you guys. So physics 1 note first I completed, and that's what you had if you took physics 1 with me. So far you are getting notes from me for physics 2 as well. But now, so I started working last year and then worked a lot during the winter. But now it is kind of, where now, I'm kind of getting behind on them. So I have to first write the note, and from the note I have to generate the question, right? So I have to write question and so on. So for the Thursday class, probably I'll be posting the pre-class assignment for the Thursday on Saturday sometimes or Sunday. Okay, so if you don't see it by Friday, so usually I do that by Friday, but if you don't see that by Friday this time, uh, wait until Saturday or Sunday. Okay, so just wanted to let you know. But the weekly gonna be come up, if not today, by tomorrow morning. Okay, weekly assignment gonna be up, but the pre-class for the Thursday could be a little late. Okay, so these are different spectrum. So gamma rays, they are generated through the radioactive material. Here in the lab you can generate X-rays using machines, right? And then light bulb generates the visible light, and infrared comes from our body. Okay, heat that's coming, that is infra, that heat hotness of our body generates the infrared radiation, okay? And if you are sitting next to fireplace, you can see the light. So that means that's a visible, and you can also feel the warmness, right? And that is infrared. And then the microwave and the radio waves, okay? So radio waves are generated through the antenna. I'll talk about antenna pretty soon, okay? Microwave, there is device. But all these radiations can also be found in our cosmos, okay? And those sources are, I have, those sources I have listed. The visible, ultraviolet, and infrared, those basically comes from the source sun, okay? And some infrared as well. And planets, they have temperature just like our body has temperature, so they can generate infrared as well. So we study all these cosmic material by receiving or detecting and analyzing the signal from them. Okay, so that's how we learn so much about this universe, although it is really huge. Okay, so now, how are those electromagnetic waves can be generated here in the lab, right? So before we talk about that, let's talk a little bit about intensity, right? So we talked about intensity of sound wave, and we said, okay, it depends on the amplitude. So in this case, it is either electric field or the magnetic field that's vibrating. So that means the intensity must depend on those. So this is just the general definition of intensity. We wrote that for the sound wave as well. So amplitude for the the electric field is E and subscript 0. And same thing goes with the magnetic field with the B. So remember, the amplitude comes out as a E0 square, but E and B are related through the C. So that's why the amplitude can be written in different ways. So like combination of both electric and magnetic field amplitude, or just write pure in terms of electric field, or write pure in terms of magnetic field. Okay. So when you write pure in terms of electric field or magnetic field, it's easy to see there is a square. Here, the square is not obvious, but once we know E and B, they are related, proportional. So that means this is also like a square thingy. Like it's like writing x squared as a x times x. Okay. So these are intensity equations. So again, it simply depends on amplitude and this is permeability of the medium, or we can write this in terms of uh, permittivity as well, as Maxwell showed us. These things are related, epsilon naught and mu naught. If you know mu naught, you can figure out epsilon naught for that material, because C is constant. Means if you know one of these, you can calculate another one. So that's why you may see different kind of equations written for the intensity, but all these are same or related. And how you can relate them? Using this equation and this equation. Okay. So remember when we were talking about EMF and current that is alternating, we had wave something like that, and then we defined RMS value. So for this, we're not defining RMS value, but we can write the average value, and average value is exactly half of the amplitude. The average turns out to be half of this amplitude. So you see this, and this is exactly half of that. Okay. So now about the antennas, how do they generate, how they work? So in the old days, there used to be antenna attached to the TV. You can still use antenna and, you know, capture the local broadcast like ABC, CBS, PBS, Fox, those local broadcasts. You can capture them using antenna. So how does they broadcast? So they put their signal, their broadcast, on top of this electromagnetic wave. So they generate electromagnetic waves and combine their signal with the electromagnetic wave. So how do they do it? Remember, the charge oscillate. When charge oscillate, what happens? It can generate electromagnetic wave. So to make that charge oscillate, they just drive this with the alternating current source, right? So that means the charges are oscillating, moving, going one way versus another way, right? So that's like oscillating. So this oscillation generates, let's say, electric field, and electric field is oscillating vertical here, and magnetic field is oscillating horizontal here. So that's what I'm trying to show you. So that's how they generate. Once it is generated, they starts moving in all direction, right? So all you need is another antenna, okay? And you can capture that. So that wave, when that wave hits the antenna, now receiving antenna, then it's going to generate current, and there is a circuit inside our device that analyze that current and then converts that to image and the sound signal. So that's how we hear, that's how we can watch TV and so on. So that's how it works, folks. Okay, so here is this question. So let's hold that quickly. Let's see if we can do that in a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly B, and that is correct. And because intensity is inverse square, but here question is talking about amplitude. So that means amplitude and distance, they are inversely related. So because of that, when distance double, it becomes only half. But if the question was about intensity, then the answer would have been 2 millivolt per meter, okay? This quarter, I should say. Okay, distance double, it became half, not quarter, because it's talking about amplitude, because amplitude is, intensity is amplitude square. So last topic in this one is polarization. So probably you are familiar with polarized glass. So what happens? The electric or the light or the electromagnetic radiation, the oscillation are taking place in all directions. Okay, so what polarized means is you block all of them and let them pass only the oscillation that's taking place in a particular direction, right? So here you see only the vertical direction are allowed, and if you put another slit something like this one gets blocked. Okay, so that's how we know, they can be polarized. So this is another example. And sunglasses do the same thing. So they cut up the random part and just let a particular direction in. That way it eliminates the glare. Okay, so glare gets eliminated when you have polarized glasses. So now if you want to know whether a glass is polarized or not, if you have two of them, what you can do is you can stack one top of another one and then rotate it, one of them, rotate it. And if it completely blocks like this, and that means they are polarized glasses, okay, polarizer. So anyway, so that's what that is, and it is already 50, so I have to let you go. So I'll see you folks next class, and we'll talk more about light in the next class. Okay, see you next week.